In order to estimate the energy from the sun, let us try to understand the sun's spectrum. So let me introduce the term spectral irradiance, PS. The spectral irradiance has the units kilowatt per meter square per unit wavelength. So generally the sun's spectrum is given in terms of this spectral irradiance, which is generally denoted kilowatt per meter square per nanometer or per micrometer, depending upon the units used for measuring the wavelengths. So typically the sun's spectrum will look like this. You have a graph, x and y axis. Let the x axis be denoted by lambda. Lambda is the symbol used to denote wavelength, and the y axis is the spectral irradiance, as we see denoted by this unit. The shape of the sun spectrum is something like this. It's an approximate. I will later on show you a more exact spectrum, but the general shape is in this fashion. So we can denote it by three important regions. So this first region is called the UV region. This is the UV region. And the second region is called the visible light region. And the third region is called the infrared region. Now these regions are basically defined by the nature of the wavelength. So if you take the UV region has wavelengths which are very small. They are very high frequency. The visible region have intermediate wavelengths, and in the case of the infrared region, the wavelengths are pretty long, very large, and the frequency is low. So the sun spectrum spans the ultraviolet to the infrared, and the visible region portion of the wavelengths is the one which is perceived by our eyes, and we can see this light. It's a visible light. However, energy content is there with respect to other wavelengths also. Importantly, note that now let us say that if I denote the wavelength as nanometer, nm, the UV region is approximately up to around 400 nanometers. 400 nanometers to around 700 nanometers is the visible spectrum. And beyond 700 nanometers, maybe up to around 4000 nanometers, you have the infrared spectrum. So these are the thermal regions. This is the visible, and this is the ultraviolet region. So note that each wavelength in the spectrum has a distinct power level. So solar radiation is an electromagnetic radiation, and each wavelength has a distinct power level. Now that can be seen from this curve itself. And all these wavelengths are felt at the surface of the earth, and it is a kind of a cumulative effect, or the accumulated effect of all the wavelengths put together. So the accumulated effect of all wavelengths together is called insolation, and the insolation is denoted by the symbol L, and L is actually an accumulation of the spectral irradiance, and therefore we can use the integral symbol, the spectral irradiance, and it is integrated with respect to the wavelength parameter delta. So which basically means that the area under this portion would indicate insolation of the ultraviolet region. The wavelength, the area under this portion of the spectrum, all the wavelengths corresponding to this portion of the spectrum would give an accumulated effect, and that is called the visible insolation. Likewise, the accumulated effect of all the wavelengths in these parts of the spectrum would give you the infrared insolation. The accumulated effect of all these put together is what we call as insolation, and given by this L, which is integral of Ps d lambda. Observe that Ps here as the units of kilowatt per meter square per unit wavelength, which is kilowatt per meter square per nanometer, corresponding to this particular graph, and L is an integral of Ps with respect to the lambda parameter, and therefore the insolation has the units of kilowatt per meter square. So remember these units. We will be using insolation quite frequently in future. Now this particular graph, the spectrum that I have drawn by hand, gives you a considerable amount of insight to the nature of the spectral energy from the sun. Now I will show you an actual spectrum with real data, and it will give you much better insight about the solar energy, about the sun energy. For this, I have collected real data and put them into a text file, which I will call from within Octave, and plot the wavelength versus the spectral irradiance. In order to understand the solar spectrum with real data, let us go to Google and type in some keywords like solar spectrum data. You will see a lot of websites getting popped up. Something interesting is to see these images. There are a whole lot of images on the solar spectrum. Just along the lines that we discussed, you can look at these images and get a lot of insight. However, these are images, these are pictures. You cannot work with the data. So we are looking at something where we can work with the data, where the data is available in numerical values. There is one site, one of the sites here, where they have collated the data and made it available in downloadable form as an XLS file, spreadsheet file, also as compressed text files, which is compatible with PC, Unix, and Macintosh. Let me download this Unix version. So a text file gets downloaded like this. Let me go and look at the folder where such a file has been downloaded and look within the compressed file. So there is a CSV file. Let us see what's inside the CSV file. So open the CSV file in a text editor and let us zoom the text. You see that it has a lot of data values comma separated data values. There's a comma and then there is again data, comma. So you have in a row 4 data values. Now the first data value is actually the wavelength in nanometer. The second data value is the extraterrestrial radiation in watts per meter square per nanometer. So these two data values are the ones of interest to us. We will only take those values and work on them. Now, before we work on these data values, let us convert this file, let us edit this file into a MATLAB compatible or an Octave compatible M file. Octave is an open source equivalent of MATLAB. So what we do is that we just convert by simple text edits. I will convert this first line into a comment line. I will put a comment line here and introduce the website URL from where we took this file, and I will make this as a comment line like this, and introduce a variable called sol and put a open bracket for the matrix. What it basically means is that all these data values are put into a matrix. What I will do, I will go down, right down to the bottom and put the close matrix brackets, and that's it. Now you have a fully MATLAB compatible or an Octave compatible file which can be worked with within the environment of Octave or MATLAB. So all these data are put into a matrix and they are named sol. So sol will basically have 4 columns and as many rows as the data provided here. What we have to now do is that change this .csv into .m. We will save this, close, and rename this as data.m. So now data.m is a MATLAB file where you can call in MATLAB and execute it. So if you look at it, now you see that this is nothing but a regular MATLAB file with sol as the variable, and sol is a matrix variable having 4 columns of data and many rows, and this is what we will be using, and we will be using only the first 2 columns of sol. The first column represents the wavelength, second column represents the spectral irradiance. I now have another script file, insolation.m. The job of this script file is to take the data values from within data.m and then appropriately use them to plot our spectrum. So data will be called by insolation and the spectral irradiance, the spectrum, will be plotted. So let us see what is within this insolation.m file quickly. So I will double click that and let me increase the zoom in the text. So quickly I will read through. This is a very simple script file. The script for plotting irradiance and solar insolation of the solar spectrum, and the solar measurement data is in data.m, which we just now created. So first, to clear all the variables in the workspace, load the data from the text file data.m by just calling data, which we just created. So it will put all the data values into the variable sol. Now lambda, a Newton meter, will be taken from the first column of sol. So all rows first column, and from all rows second column of sol you will obtain the spectral irradiance data. Now the spectral irradiance data is given in watts per meter square per nanometer. So I have just commented, I put a comment here so that it is good for readability. Now the last line here is a plot statement which plots lambda, that is the wavelength, versus spectral irradiance, and grid, the X label, Y label, and the title are also included. Now let us run this in Octave and see what happens. So let me open Octave. So this is the Octave environment. Let me clear the workspace screen. Let me go in here into the appropriate folder with the solar spectrum folder. It has these files. I have to run insolation script. So let me type in insolation, and it will plot the data values accordingly like this. Let me zoom this, and you see that this is the solar irradiance spectrum. This is actually PS in watts per meter square per nanometer, and the x-axis is the wavelength. It goes up to 4000 nanometer. Observe here, let me just use it as a marker. Observe that somewhere around here will be between 400 nanometers and 700 nanometers, and this is the visible spectrum, what I have marked here in the rectangle. To the left of it will be the ultraviolet region of the spectrum, and to the right of this rectangle will be the infrared region of the spectrum. Let us now write few more lines in the insolation.m file such that we are able to integrate this PS curve and obtain the insolation curve also and superimpose on this graph. Let me go back again into the insolation.m file in the text editor. Let me introduce few more lines of code here. So we have to integrate the irradiance column. So integrate the spectral irradiance PS so that we may obtain L, the integration with respect to the lambda parameter. I have used here a simple trapezoidal integration which is of this form, and all these lines are basically integrating the spectral irradiance to obtain finally the insolation in the variable insol. Now the insolation is also actually in watts per meter square because the data given is in watts per meter square per nanometer. Therefore insolation also is in watts per meter square. However, while displaying, what I can do is, let me display in this fashion: plot lambda, that is the wavelength, and the spectral irradiance, wavelength and the insolation, but insolation I am dividing by 1000 so that we can output the insolation in terms of kilowatt per meter square. So the wavelength, the Y label has irradiance in watts per meter square per Newton meter, and insolation in kilowatt per meter square because I have divided that by 1000. So let us see the old plot statement I will remove. So this would be the modified file. Let me save this and let us execute that. So we go in here. And let me type in insolation. So when you type in insolation, now you see that we see the graph of both the spectral irradiance, the blue curve, and there is this green curve which is the integrated value of the spectral irradiance along the lambda axis. Now see, it integrates to around 1.3. Let me just zoom at that point, then you will get the value. So here you see that it has integrated to around 1.347, like that. Always remember that the solar insolation would integrate to between 1.33 kilowatt per meter square to 1.41 kilowatt per meter square, and it depends upon the day of the year, and this is because of the elliptic orbit of the earth around the sun. So therefore this variation. Generally in the literature, an average value, the mean value between 1.33 and 1.37 is taken as the solar constant. So if you hear the term solar constant, it means it is 1.37 kilowatt per meter square. So always the insolation value L will integrate to a number between these two. So that is the takeaway out of this figure. So I will keep this data.m file containing the data and the insolation.m containing the script for utilizing this data and plotting the irradiance and the insolation in the resource section, so that you can download this source as a zip file, and then you can run them, operate on them, and then gain some insight out of this.